Welcome back to Tech with Kaushik, where we build your deep understanding of how AI actually works. I'm Kaushik. If you watched our RAG video, you learned how AI can search for knowledge to ground itself in truth. Today, we're going deeper into the actual mechanics of how that search works. We're going to trace a single sentence. The king wore a crown. Watch this sentence. Hold on to it. This isn't a random example. It's about to take a journey through an AI's mind, and by the end of this video, you'll understand exactly where it goes. This journey will show you how AI turns words into meaning you can actually measure. Here's a question that nobody ever answers, but it's worth asking. When you ask an AI, what do king and queen have in common? The AI instantly knows they're similar, related, connected. But nobody ever told the AI that. There's no rule in the training data that says king and queen are alike. So how does it know? The answer is what we're about to explore. Our sentence starts here. The king wore a crown. The first thing that happens, it gets chopped. Not into individual letters. Not into a whole block. Into tokens. Think of them as meaningful chunks. The is one chunk. King is one chunk. War is one chunk. A is one chunk. Crown is one chunk. These chunks are what the AI actually reads. Not letters. Not words exactly. Tokens. And each token gets assigned a number. A reference ID. Just a name tag. You might wonder, why not just treat every word as one chunk? Because some words are rare, new, made up. Imagine you write Kingstonify, a word that doesn't exist in the AI's training data. The AI can't treat it as one token because it's never seen that exact word. So instead, it breaks it down into pieces it knows. King, that's a token. Ston, another token. Ife, a third token. This way, the AI can handle any word it encounters. Common or rare, it breaks it down into manageable pieces. That's tokenization. So our sentence becomes a list of numbers. The equals 402. King equals 5831. War equals 2019. A equals 1. Crown equals 6472. These are just reference IDs, like name tags. But here's the thing. The numbers themselves don't mean anything yet. 402 and 403 being close doesn't mean those tokens are similar. It's just a numbering system. The real magic comes next. Plain ID numbers don't carry meaning. You could ask the AI, does token 402 relate to token 403? And the answer is, who knows? They're just sequential numbers. The ID doesn't tell you anything about whether those words are similar in meaning. We need a different representation, a way to encode meaning itself into numbers. Not just what's your reference ID, but what do you mean? Here's the breakthrough. Instead of representing each token with one number, represent it with a list of numbers. A whole array. King isn't just 5831. It becomes something like 0.8 minus 0.3, 0.5, 0.9, 0.2. That's 300 plus numbers. Hundreds of values. All describing different aspects of what king means. One number can't capture meaning, but hundreds of numbers? They can. This list of numbers is called an embedding. This might sound strange, so let me make it concrete. Think of describing a person. You might use three numbers. Height is 180 centimeters. Age is 35 years old. Mood is happy. Those three numbers are like coordinates in 3D space. They place that person at a specific location in a three-dimensional world defined by height, age, and mood. Now, a word works the same way, except instead of 3 dimensions, it has hundreds. King might be described by royalness 0.9, masculine 0.8, powerful 0.85, and 297 other meaning dimensions. Both a person and a word are just points in space. The person in 3D space, the word in 300-dimensional space. Same principle, different scale. When you plot all these vectors in space, all these points of meaning, something magical happens. Similar words cluster together. King floats near queen, prince, royal, crown. Peasant is nearby but farther. Warrior is across the neighborhood. And banana? It's on the other side of the galaxy. This is the meaning space. And here's the beautiful part. The distance between 2 points in this space roughly measures how similar they are in meaning. Close words have related meanings. Far words are unrelated. That's how the AI knows that king and queen are similar. They're positioned near each other in this space. There's a famous example that demonstrates this, and it's best shown geometrically, not mathematically. Imagine 4 points in this meaning space: king, man, woman, queen. There's a directional relationship. If you travel from king in one direction, you get to man. If you travel from queen in the same direction, you get to woman. In other words, the direction from king to man is parallel to the direction from queen to woman. This captures a real semantic truth. King is to man as queen is to woman. The geometry of meaning space lets us see these relationships clearly. No formulas needed, just geometry. Now that we have words as points in space, we need a way to measure the distance between them. That measurement is called semantic similarity. It's a number between 0 and 1. 0 means completely different, no shared meaning whatsoever. 1 means identical or nearly identical meaning. Between 0 and 1, various degrees of relatedness. King and queen might have a similarity of 0.95, nearly identical meaning. King and banana might have a similarity of 0.02, completely unrelated. This number is what allows AI to understand which documents are relevant to a query. If this visualization is clicking for you, do me a favor, hit like and subscribe to Tech with Kaushik so you don't miss how we actually use this to build AI systems. Here's the intuition for how similarity is measured. Imagine you're in a dark room. 2 flashlights both start from the same point, the origin. One flashlight points northeast. That's the direction of king. Another flashlight points north-northeast. That's the direction of queen. These directions are nearly parallel. They're pointing almost the same way. Cosine Similarity asks, how aligned are these directions? If 2 flashlights point the same direction, they're perfectly aligned. If they point at a 90-degree angle to each other, they're completely misaligned. The angle between them tells you the similarity. Small angle equals similar. Big angle equals different. Let me show you 3 scenarios. Scenario 1. 2 flashlights pointing nearly the same direction. Angle between them, about 5 degrees. This represents king and queen. Cosine similarity, 0.95. Very similar. Scenario 2. 2 flashlights at a right angle to each other. Angle between them, 90 degrees. This represents king and computer. Cosine similarity, 0.0. Completely unrelated. Scenario 3. 2 flashlights pointing opposite directions. Angle between them, 180 degrees. This represents good and bad. Cosine similarity, -1.0. Opposite meanings. Cosine similarity measures the angle between 2 vectors. That angle captures their semantic relationship. Here's a direct comparison. Top, king and queen, vectors pointing nearly the same direction. The angle between them, very small, maybe 5 to 10 degrees. Cosine similarity, 0.95. Bottom, king and banana, vectors pointing in very different directions. The angle between them, very large, maybe 85 to 90 degrees. Cosine similarity, 0.05. See the difference? It's all about the angle. And here's what's beautiful. This isn't about how long the vectors are. A short sentence and a long sentence can point the same direction. Cosine similarity only cares about direction, not magnitude. This is an important point. Why measure direction and ignore magnitude? Imagine 2 sentences. Sentence 1, the king. Sentence 2, the king wore a magnificent crown and carried a golden scepter through the grand hall. These are very different lengths, but they both describe the same thing, royalty, a monarch. So in meaning space, they should point the same direction. The first sentence has a shorter vector. The second has a longer vector. But their angles? Nearly identical. Cosine similarity captures this. It says, yes, these 2 sentences mean the same thing, even though one is short and one is long. That's why we measure angle, not distance from the origin. Here's where this matters in the real world. Imagine you're searching a medical database. You search for side effect. With old keyword search, the system looks for documents containing exactly side effect. A document titled Adverse Reaction to Medication gets missed. It doesn't contain the words side effect. A document titled Negative Outcome gets missed. Different words. A document titled Unwanted Consequence gets missed. Again, different exact words. With semantic search, the kind powered by embeddings and cosine similarity, everything changes. Your query side effect gets converted to a vector in meaning space. All the documents, adverse reaction, negative outcome, unwanted consequence, also get converted to vectors. The system finds all vectors similar to your query vector. Now all three documents are found because they mean the same thing, even if the words are different. That's the power of semantic search. And here's the bridge to what you learned about RAG in the previous video. Everything you just learned, tokenization, embeddings, semantic similarity, cosine angle measurement, is exactly how RAG systems search for relevant documents. RAG converts your question to an embedding. RAG converts all the documents in its knowledge base to embeddings. RAG measures the cosine similarity between your question and each document. RAG retrieves the most similar documents. That's how RAG grounds AI responses in truth. But we're not done yet. We still need to solve the scale problem. Here's a problem that nobody talks about, but it's huge. Let's say you have a document database. 1 billion documents. Each one has an embedding. Someone asks a question. That question gets embedded. Now you need to find the most similar documents. If you compared that one query embedding to every single document embedding one by one, that's 1 billion comparisons. On a fast computer? 5 hours. 10 billion documents? 50 hours. 100 billion? 500 hours. This isn't practical. This isn't scalable. You need a smarter way. You need a shortcut. This is where vector databases come in. A vector database is built specifically to solve this scale problem. Instead of comparing a query to every single vector one by one, the vector database uses shortcuts. It organizes all the vectors into clusters and hierarchies. When a query comes in, the database uses these shortcuts to jump directly to the relevant clusters. Instead of checking a billion vectors, it checks maybe 1,000. Instead of 5 hours, it takes milliseconds. This is one of the most clever pieces of modern AI infrastructure. And it's all because we solved an interesting mathematical problem: how to find the nearest neighbors in high-dimensional space fast. Think of it like a city. Old approach. You want to find your friend across the city, so you check every single street, every single building, one by one. That's slow. Vector database approach. There's a highway system. Major routes connecting neighborhoods. You want to find your friend? Use the highway map. Jump to the right neighborhood, then search locally. Instant. The vector database creates a highway system through the space of all possible embeddings. It maps where vectors cluster, where similar meanings congregate. When a query comes in, it uses this map to navigate. There's a technical name for one such system: HNSW, Hierarchical Navigable Small World. But the principle is the same, a shortcut system built into the database. Let's trace our sentence's complete journey. The king wore a crown. Step 1, tokenization. The sentence gets chopped into tokens. Each gets an ID number. Step 2, embeddings. Each token ID becomes a list of numbers, vectors that carry meaning. Step 3, semantic space. These vectors get positioned in high-dimensional space. Similar words cluster together. Step 4, cosine similarity. The angle between vectors measures their relationship. Step 5, vector database. These vectors get organized into a searchable, queryable system. Step 6, instant retrieval. A new query comes in, gets embedded, uses the vector database's shortcuts to find the closest matches in milliseconds. A sentence has been transformed from text into retrievable, measurable, comparable meaning. That's the translation machine. Remember these 5 things. 1. Tokens are language chopped into machine-readable pieces. 2. Embeddings are lists of numbers that carry meaning. 3. Semantic similarity measures closeness in meaning. 4. Cosine similarity uses angle, direction, not distance or magnitude. 5. Vector databases are fast retrieval systems for billions of meanings. This is how AI knows that king and queen are similar. This is how RAG finds relevant documents. This is how modern AI search actually works. If this understanding of the architecture just changed how you think about AI, hit like and subscribe to Tech with Kaushik for more on AI, vector databases, and the technology behind the scenes. Your understanding just went from surface level to architectural. Thanks for watching.